So our next speaker will be Saida Nasim. So Saida graduated from the City University of New York in 2018, and since then has been working at the American Museum of Natural History. Um, and Saida will be starting graduate school at the Missouri University of Science and Technology in the fall. Congratulations to her. Um, so today
Thank
she'll
you.
be telling us about photon trajectories in curved spacetime based on her work with her mentors, Doctors Konstantinos Kalaportharakos and Dr. Zoravar Wadiasing. Um, and they have the following to say about Zaida. So they say that she was enjoyable to work with over the summer. She absorbed a significant amount of information quickly and understood complex concepts from papers at the graduate level, despite never having taken a course in general relativity. She also handled the challenge of developing a Python ray tracing code from scratch and interacting remotely during the pandemic well, and we are very proud of her. Depending on her plans, we plan to continue to collaborate on projects in the future. So it looks like Saida, you're going to have a very busy fall. So with that, the floor is yours. Um, Feel free to share your screen whenever.
Thank you. Um, so are you guys able to see my slides?
Yes, we can see it. There is a
Is the Zoom?
bit of a pop-up. There we
Okay,
go.
that's the Zoom window. Okay, cool.
Awesome. Okay.
Um, okay, great. All right, so hello. My name is Saida Nasim, and this summer, as Andrew mentioned, I worked with Dr. Konstantinos Kalapatheros and Dr. Zoravar Wadising on photon tracing in curved space-time. Specifically, we traced light rays around neutron stars, which are these extremely compact stellar remnants. Um, yeah, so I wanted to talk a little bit about the motivation for like studying the photon trajectories around neutron stars. So that has a little bit to do with a lot to do with the NICER telescope. The NICER telescope, or the Neutron Star Interior Composition Explorer, its motivation is to understand the microscopic behavior of matter inside of neutron stars. And the reason why this is an interesting problem that we'd like to understand better is the inside of these neutron stars are they have a pressure and density that are higher than that within atomic nuclei. So on one hand, you have the gravity that's pulling everything together, and on the other hand, you have the repulsion between the protons and neutrons, and we're sort of trying to demystify how that matter behaves. So one way that we aim to do this is by understanding the relationship between the mass and the radius of the star, because this relationship between mass and radius is equivalent to the relationship between the star's density and pressure. And this tells us in turn the equation of state. And the equation of state is what will eventually, understanding the equation of state is what will eventually let us understand the microscopic properties of matter inside of the stars. So yeah, a little bit about this figure here, where every line essentially represents different models for these neutrons, for the mass radius relationship for neutron stars. And a lot of them have a very similar wonky number 2 shape, where we find that the radius is consistent across most of the mass range, which we also stick to in our simulations for the purposes of this project. I think it's a little interesting to note that although they look like all of these models, or most of these models, look like they're slightly offset from each other, I think it's important to note that those small offsets can have big implications for how how the matter can behave inside of these stars. Okay, enough about that. It's not just the inside of these stars or these objects that are affected by this extreme compactness. There is an external influence too. So we call this gravitational lensing, where the extreme gravity causes light to the paths of light to bend when they're close to these stars. We also see this with black holes, which is interesting. If I'm sure that most of you are familiar with this sort of image of a black hole and its accretion disk. So like it's a little bit confusing when you see this for the first time. It looks like there is like a part of the disk that goes above and below the black hole, which is actually not what's happening. What's happening is that the part in the middle is actually the part of the disk passing in front of the black hole, and the part above and below are just the disk that's passing behind the black hole. But because of the distortion of light, it looks like it's coming from above and below, but it's really behind. So that's a bit more of an extreme example. But with neutron stars, which have actual surfaces, we're talking about seeing light emitted from behind the back of the star or the far side of the star. So in this image from Nullert et al. 1988, if you can imagine an observer here on the right-hand part of the slide, they're just hanging out. They can see everything on the right-hand side of the star. If this was a regular star, that's all they'd see. But we're a neutron star and we're special and we're wearing our quadrupole moments and we want to show off and we want to show more. So we do. And these lines actually represent like the paths of light. It's like, tracing the light rays. So these two rays in particular are actually light from the far side of the star, the left side of the star in this case, that reach the observer anyway, which is like sort of like what we're aiming to like study in our in my project. So here are some more figures from the same paper, and this is actually what the observer sees. So in the previous slide, we saw how the light bends, and these figures sort of show how that translates into an image that we see as an observer. So actually, this teal circle sort of represents the actual part of the star that's facing us as an observer, and everything outside of that is actually an image of the far side of the star. So that's it's like, it looks like it's just a regular globe, but it's not. It's more. Yeah. And so why do we care about this? Well, these little black dots that we're seeing depict something called hotspots. Hotspots are regions on a stellar surface where its magnetic field lines are open. And the reason why we care about that is, in the case of neutron stars, the light that we see from neutron stars observationally they originate from these regions on the stellar surface. So in this figure, actually, we're seeing two hotspots, like say this guy, and we're seeing how it looks different during different phases in the star's rotation along its axis, which is like sort of like one of the things that we'd ultimately like to implement in my work. Okay, so on to like my actual project and things that I did. We use these four simultaneous coupled ODEs from Saltis and Johansen 2012. These are geodesic equations that ultimately will give us the photon trajectory or path of light from the neutron star. The first set of these are first order equations, and the second set of these are second order equations. But in order to implement this in Python using the function that we use, the solve IVP function, we had to convert these second order ODEs into first order ODEs. So how did we do that? We made a very, very silly manipulation or substitution where we exploited the relationship between position and velocity and acceleration. Basically, the second derivative of position is just equal to the first derivative of velocity. So that's how we ended up getting first order equation. So we started off with 4 equations, and now we have 6 in total. So 1, 2, 3, 4, 5, 6. And yeah, so ultimately, what does that do? So here is another, here's a figure from another paper, from a follow-up paper that sort of depicts like what the code is doing. So this image plane is actually the observer plane. You can imagine that this is where we're looking at the star from. And the D here represents the distance between us and the star. This theta naught, or we refer to as zeta going forward, is like the inclination of the star's rotational axis with respect to our line of sight. So basically, whether its rotational axis is pointing directly at us or away from us. And alpha beta tells us essentially how big our observer plane is. And technically, when we observe things, the light is coming from the star to us, but we trace the light backwards. Okay, so this is sort of a schematic, so this is like basically like a bunch of pixels. So like 50 by 50 pixels, which means that like there's, in this case, 2,500 individual points on this observer plane, and each of those points represents one light trajectory. And some of those trajectories will hit the star, and some of those will miss the star. And this is sort of just like a cool PowerPoint animation. It's not a real sorry. But in the next slide, what we have are the actual calculated light trajectories, and the teal represents points that hit the star, and the gray represents points that miss the star. So how does this translate into images for the observer? So we look at a couple of different things, like how changing the observer angle affects what we see. So on this left-hand animation, we're just seeing that as we change how inclined the star is with respect to our line of sight, how the image changes. And in this next panel, we're just rotating the star to see how it looks along different phases of its rotation. Here we have these animations, they depict what happens when we increase the mass of the star, how what we see changes. But while we increase the mass of the star, we're also conserving the mass radius ratio. So while the mass is increasing, the radius is increasing accordingly. So what we see here is, this is what the observer sees, and we're plotting the same grid lines onto like a schematic star and like rotating at 90 degrees. So this shows us like the fraction of the star that we actually see. So it's a little bit more than half of the star that we're seeing. And you'll notice that even though the star is physically getting bigger as we increase the mass radius ratio, we're not seeing any more of the star. We're just seeing the same amount, even though the star's size is changing, and that's why the image is getting bigger. In this next figure, we're changing the mass radius ratio. So we're increasing the mass, but we're keeping the radius constant at 12 kilometers. And what we see, oh, sorry, let me try that again. Okay, I'm so sorry. My animations. Okay. There we go. Okay, so here we're changing the mass radius ratio. So we're keeping the radius constant, but we're increasing the mass. And what we find is that the image is increasing, like the amount that the star, it looks like it's growing as an observer. But when you look at how that maps onto the star, you see that the star's size is remaining constant, and we're just seeing more and more of the star until this very last frame, actually, when we go up to a little bit of a ridiculously high solar mass, we can see the whole star, including its like the front and the back of the star. And this is sort of just that last panel of that animation. And I just wanted to show like how different resolutions, so depending on how many pixels that you choose, how the image of the star gets a little bit better. So here is like 400 by 400 pixels, and here we have 1,000 by 1,000. And if you pay attention to like the poles of the star and the very edges of the star, you can see that it's a lot smoother. Yeah. Okay. And broader impacts. So these are not plots that I've made. These are plots from a paper that sort of speak to future work that I'd like to do with this. So like I mentioned before, hotspots are the regions on the stellar surface where the light we see is emitted from. So I'd like to plot these geometrically simple hotspots and like sort of be able to distinguish between which light rays that are emitted from the star are emitted from these regions specifically. And ultimately, I'd like to be able to make sort of a light curve that shows that and being able to like make these light curves will ultimately help us to understand the light curves that we're getting from the NICER telescope. So the NICER telescope has really, really good observations. And the point of doing all of these simulations is sort of to, for our theory to match our observations. And we want to resolve things like the shapes and positions of these hotspots, but also other things go into these light curves, like, for example, the redshift and the spin of the star and the oblateness of the star and different wavelengths of light that are emitted from the star. All of those things are things that we have to consider for these light curves. And ultimately understanding that will help us to exploit NICER data. And that's sort of all I've got. Yeah, thank you.
Thanks so much, Saida. That was a fantastic talk.
Thank you. Was I over time?
No, you were just on time.
Awesome. Okay.
Yeah. So, anybody have any questions for us, Saida? We have 5 minutes. Charlotte, please go ahead.
Yeah, I was just I had a question about the resolution plots or like point that you made about like the the higher resolution option. I was wondering like how much it changes the computational time if you like between these two plots. Like, is that kind of a factor in what resolutions you can reach?
Yeah, that's a huge factor. Sorry, I kind of like rushed through these parts. I should have mentioned like the amount of like pixels that we choose to simulate in our observer plane like has a really big impact on the time. So like there's the amount of time that it takes to do an individual trajectory, which could be a fraction of a second. And when you have an observer plane, if I go back here, each of these plots, each of these points represents an individual trajectory. So if we do like, for example, 50 by 50, we can get an image in a reasonable amount of time. But because that's like what 2,500 points or trajectories. But if we do, for example, 1,000 by 1,000, like we did like here in this right hand plot, that's a million trajectories, and that can take a pretty substantial amount of time just to get like this one image. And then if we want to like make an animation where there are maybe like 20 or 30 frames, that's going to multiply that by that many times. So like it's like making the code efficient has been like a big part of this project. So we used a couple of different methods to try to make the computations more efficient. And one of the tools that we used was Nemba. Yeah, I hope that sort of helps.
Yeah, definitely. Thank you.
Okay, cool. Any more questions?
If there are no more questions, then we can thank Saida again, as well as her mentors, Konstantinos and Zoroar, for really fantastic work. And all of those little plots and animations must have taken up so much time to make, so brilliantly done again.
Thank you.
I guess now we can pass it on to Charlotte, who will introduce the next speaker.